Okay, hello and welcome to Symbolic Logic Unit 9, Natural Deduction and Conjunction and Disjunction. So today we're going to be continuing on the discussion that we started last time in Unit 8. Recall there that we talked about truth tables and how truth tables had certain benefits but also a number of drawbacks. The benefits were that they could prove validity, consistency, and equivalency in a systematic way, in a purely deductive way that didn't require any creativity whatsoever. But the drawback was that this method required more rows the more atomic sentences we have. So for example, with 6 atomic sentences composing an argument, we would require 64 rows. 7 would require 128 rows. Additionally, these require lots of columns with more premises. So it could be that our tables would be longer than a single sheet of paper. These also don't resemble informal reasoning from principles. They don't seem to work like human reasoning typically does, but instead require us to think about these complex matrices and where statements turn out true and false. And finally, these can show us that an inference is truth-preserving. In other words, that you can infer some conclusion accurately from some premises, but truth tables don't explain why that pattern of inference is truth-preserving. So the method we're investigating now is called the method of natural deduction. And the method of natural deduction is in some ways meant to mirror human reasoning, although you may think that the inferences we're allowed to draw using this method are fairly basic. And additionally, it should allow us to tell how the conclusions that we get are actually derived in a very basic way from premises. So in this way, it far surpasses the truth table method. So the general idea with natural deduction is that we're going to start with the premises of an argument and apply rules that we have developed that we know preserve truth to arrive at the conclusion of the argument. And we do this by applying the rules step by step to derive further steps in our argument. Okay, so here's an example. So we have here a Fitch line with some premises drawn above the Fitch bar, and we know that eventually we're going to derive the conclusion from a certain rule here. We may not know where exactly to put the conclusion, but we want to be mindful that this is where we want to end up, whatever this sentence happens to be. So we have the premises. We, of course, need to number each line on the left side of the Fitch bar. And so in these examples, I'll also use letters to represent numbers when we don't know how far down and how many steps we're going to need to arrive at a conclusion, for example. So the letters will be variables for numbers for lines. Okay, so we start with our premises. And then in between this, we're going to write additional steps, each representing the application of a rule to premises and the intermediate inferences that we draw from those premises on our route to the conclusion. So for example, we might draw 2 inferences from our premises, applying rules along the way, some more inferences and some more inferences, until finally we reach the conclusion. And you stop when you've used the rules to generate the conclusion that you're after. So this is a way of showing a pattern of reasoning that leads us from some premises to a conclusion. In other words, this allows us to appreciate not only that an argument is valid, but the various steps along the way that get us to the conclusion in a valid, that is, truth-preserving fashion. Okay, let's look at an example filled out a little bit more. So suppose, for example, that you want to formally prove that J follows from if it's not the case that L, then J or L, and not L. Okay, so this is what you want to show. You want to show that J follows from these things. So what we'll do is, first of all, if we were to set this up to derive this conclusion from these premises, we'd put the premises above the Fitch bar on our Fitch line, numbering them 1 and 2. So we can put as premise 1. Doesn't really matter the order they come in, but we'll make number 1, if it's not the case that L, then either J or L, and we'll make premise 2 not L. We then know that ultimately we're going to get to J. That's our conclusion. And so if this argument is valid, we should be able to derive J using only our rules of derivation, okay? So what we would do next in deriving this conclusion is we would need a step here. So the step would be J or L. And we're able to derive this step using a rule called conditional elimination. So as you can see, we move from this conditional statement to eliminate that, basically because the antecedent of that conditional, it's not the case that L, was supplied by premise 2, we were able to determine that the consequent has to be true, right? So remember, if premise 1 is true, and if its antecedent is true, then it has to follow that the consequent is true, right? Otherwise, if it's not the case that L, then J or L wouldn't have been true. So we are now able to derive J or L. And again, we do that using this rule we'll investigate later called conditional elimination. And then we cite the premises that this derives from. So it derives from premise 1 and premise 2. The premises are steps, steps. In this case, they happen to be premises. Okay, and then once we have J or L, we are able to derive J, and the way we would do that is using disjunction elimination. So this is another rule. This rule tells us, remember, we know that for a disjunction to be true, one of its disjuncts has to be true. We know now that J or L is true based upon the assumption that our premises are true. We'll always suppose our premises are true. So we know J or L, and we know that it can't be the case that L or not L from premise 2. So again, we're able to derive our desired conclusion J through a single application of the rule called disjunction elimination, and that comes from premise 2 and step 3. So that allows us to derive J, our conclusion. So this is an example of how we would do a formal proof using some basic rules of our system. And today we'll be learning about some of these basic rules. Again, these are the applications of the formal rules of our system. So this is our shorthand for saying conditional elimination from 1 and 2, and disjunction elimination from 2 and 3. So this is an important note-keeping feature of our system, and you'll want to adopt this method of showing which rules you have used to derive various steps and conclusions. And one other thing to note, and I mentioned this last time, is that there's an elimination and an introduction rule for each of our connectives. So in this case, we've used only elimination rules. We've eliminated the conditional presented in premise 1. That is, we've moved from that conditional to step 3, something that doesn't contain a conditional symbol in it. So that's why we call it elimination, because we got rid of a conditional symbol in moving from 1 and 2 to 3. And then we also used an elimination rule in 4, because we moved from the disjunction at 3 to a statement that no longer includes a disjunction. So we eliminated that disjunction using steps 2 and 3 to arrive at J in step 4. Okay, so in a sense, we're eliminating the connectives in both of these cases, but there are also introduction rules which allow us to introduce sentences containing connectives. So for our conditional rule, for our conditional connective, there is a conditional introduction rule. For disjunction, there's also a disjunction introduction rule, and we'll be learning about these as we move forward this week. Okay, so first we're going to learn about conjunctive reasoning. So we're going to learn about reasoning from a conjunction. So this is, in other words, the application of the conjunction elimination rule. All right, so here's an example to show, and for each one of these connectives, I'm going to give you examples to show this kind of reasoning and how intuitive it is, how likely it is that we think it's going to preserve truth. okay? So I'm going to give you an ordinary example to illustrate each of our rules. So again, the first rule is conjunction elimination. In other words, we're reasoning from a conjunction, moving away from a conjunctive statement. So I want you to suppose that you're wondering if cats give live birth. So you know that cats are mammals. So you look it up and find that mammals are the following, and this is a definition I took from an online dictionary. Cats are warm-blooded vertebrates, and they have hair or fur, and they give live birth, and they secrete milk for their young. So lo and behold, it follows from this definition, assuming the truth of this definition, that cats do give live birth. So what our definition taught us was this complicated thing, the following statement, that that cats are warm-blooded vertebrates and have hair or fur and give live birth and secrete milk for their young. Right? We could replace this by saying that our statement, what we learned from this definition, right? If we say that A stands for cats are warm-blooded vertebrates, B stands for cats have hair or fur, and C stands for cats give live birth, and D is cats secrete milk for their young, we could give a formal statement of this definition, replacing these atomic sentences with sentence letters, and get this statement, A and B and C and D. But what we were interested in wasn't this complicated thing, right? Instead, what we wanted to know was whether cats give live birth. And it's part of this definition, of this complex definition, that they do. So we can derive that, condition C, cats give live birth, from premise 1 here. In other words, if we have a conjunctive statement consisting of however many conjuncts, we can infer that any one of those conjuncts is true via a single use of conjunction elimination, okay? Remember, a conjunctive statement is true if and only if all of the conjuncts are true. So if we know a conjunctive statement is true, then we can validly derive any of the conjuncts. If the conjunctive statement is true, then each of the conjuncts is guaranteed to be true. So the general form of this conjunction elimination rule is as follows. So at some step M or premise, you have a statement of the following form. And remember, Greek letters are variables for sentence letters. So we have phi and psi. And now, if we have a conjunctive statement like this one, and it could have more conjuncts like A and B and C and D above, but if we have a conjunctive statement like this, we are justified in deriving either of the conjuncts, either phi or psi, from this conjunctive statement. And the reason we are, again, is that the only way for a conjunctive statement to be true is for each of its conjuncts to be true. So if we know a conjunctive statement, then we also have a guarantee that each of the conjuncts that make up that conjunctive statement are also known, are also true in their own right. Finally, one other thing to notice about our conjunction elimination rule and our rules in general is that in our general form of the rule, we see the letter M here at the end of it. And that's simply telling us, the letters that appear there are just telling us what premises or how many premises we have to cite in deriving this conclusion. So here, for conjunction elimination, we only have to cite one thing, and that is the conjunctive statement that we are eliminating to move to one of its conjuncts. Okay, so in using conjunction elimination, you will cite the step where the conjunction appears. Okay, let's turn now to look at conjunction introduction. So in conjunction elimination, we moved from a conjunctive statement to a statement that had at least one less conjunct in it. So now we're going to consider conjunctive introduction. In this case, we'll be moving towards a statement that includes a conjunction where previously there wasn't a conjunctive statement. So consider as an example the following. Gary Wendell is a mammal. which means that he's got hair or fur. Okay, so Gary Wendell has got hair or fur is true. It's also true that Gary Wendell in this picture is wearing a sweater. So it follows from these two claims that Gary Wendell has hair or fur and that Gary Wendell is wearing a sweater. In other words, if we know these two things, Gary Wendell has hair or fur and Gary Wendell is wearing a sweater, then we also know that Gary Wendell has hair or fur, conjunction Gary Wendell is wearing a sweater. Okay? So essentially what we're doing here is moving from some statement, and the first statement here was itself a complex statement, so we had X or Y. So X stands for Gary Wendell has hair, Y stood for Gary Wendell has fur, and the thing we knew originally was that Gary Wendell has hair or Gary Wendell has fur. And now we also knew from this picture that Gary Wendell is wearing a sweater. So we can conjoin that complex disjunctive statement together with the simple atomic statement, Gary Wendell is wearing a sweater, to generate this new conjunctive statement. Either X or Y and Z. So that is conjunction. That is a conjunctive statement we have derived from two non-conjunctive statements using a single application of our rule, conjunction introduction. And notice here that what we cite are the steps where the things that we ended up conjoining were in the argument above where we deploy this rule. So the general form of this conjunction introduction rule is the following. Suppose that at step M, you have the statement phi, and at step N, you have the statement psi. Then you can infer phi and psi using conjunction introduction from these two steps that occurred at M and N. And you will cite those two things or more things that end up getting conjoined in your application of this rule. Okay, so now we turn to our disjunction symbol. So we've seen two rules, a rule of introduction and a rule of elimination for our conjunctive symbol, and I hope both of those were clear how they function. So let's turn now to look at rules for disjunction. And first we're going to consider disjunction elimination, so reasoning from a disjunction to some statement that contains one less disjunction. So, okay, suppose you are wondering who won the student council election. So you know that Lisa and Carl were running. So you know a disjunctive thing, either that Lisa won or Carl won. And we can suppose they were the only people running. That's what I mean here. So you know this disjunction, Lisa won or Carl won. Later on, you hear that Carl has conceded defeat. That means it's not the case that Carl won. And it follows from it's not being the case that Carl won and that they were the two people that were running, that Lisa won. So we can infer from a disjunctive statement and the negation of one of its disjuncts that the other disjunct must be true. And this follows from our rule for disjunction that a disjunctive statement is true so long as, and only so long as, one of its disjuncts is true. So if we know a disjunctive statement follows, or we know a disjunctive statement is true, and we know one of the disjuncts is false, then it follows that the other disjunct must be true. And so that's what you infer here when you infer that Lisa won, right? So J can stand for Lisa won, K stands for Carl won. So we know that initially either Lisa won or Carl won, and now if you learn that it's not the case that Carl won, then you are in a position to infer Lisa won, and we do this via a single application of disjunction elimination from premise 1 and 2, premises 1 and 2. Okay, so here's the general form of this rule. So if we are presented with a disjunction at line M, phi or psi, and we are given at line N a negated statement, it's not the case that phi, then we are in a position to derive psi via disjunction elimination from M and N. And conversely, if we had been given phi or psi, and we had been presented with, it's not the case that psi, negation psi, then we would be justified in deriving phi via disjunction elimination from M and N. So it can go either way. We can apply disjunction elimination to derive either side of a disjunction. Okay, so that's reasoning from a disjunctive statement. Now, we might also reason to a disjunctive statement. I alluded to this in our last lesson on Unit 8, but let's look again at this. So suppose that it is true that Emiliano Zapata is a friend of the people. Okay, suppose that is a true statement. Well, we know that for a disjunction to be true, it only has to be the case that one of its disjuncts is true. So a disjunctive statement is true so long as one of its disjuncts is true. If it has more than one, they may both be true, but they needn't be one is enough. Okay, so if it is true that Emiliano Zapata is a friend of the people, then it is also true that Emiliano Zapata is a friend of the people, or that the moon is a giant turnip, right? So a disjunctive statement, again, is true if any one of its disjuncts is true. So thus, from any statement, we can infer a disjunction of that statement and any number of disjuncts, right? If that statement was true, as it will be if it was a premise or if it was derived from our true premises, then anything that is derived from that thing will also, using our rules, will also be true. And so if we attach that item to another statement via disjunction, we also get yet another true statement. So again, the general form of this rule is if we are presented at line M with a statement phi, then we can infer phi or psi via disjunction introduction, and all we have to do is cite one thing, the sentence that is the known to be true disjunct of our disjunction that we're deriving, or we can derive psi or phi, just flipping the order of that disjunctive. So the thing that's being added can go before or after the disjunction symbol. All right, so we've now learned 4 rules of symbolic logic, the 2 introduction and the 2 elimination rules for disjunction and conjunction. Okay, so the introduction elimination rule for disjunction and the introduction elimination rule for conjunction. So we can put all of these rules together, and we're going to be learning more of them, to derive a very powerful derivation system, which will allow us to move from premises to a conclusion in a valid way, in a way that preserves the truth of our conclusions on the assumption that our premises were true. Okay, so here's an example. I'm going to show you how these rules can be applied to derive some conclusion. So here's proof 1. In proof 1, we are given x and either y or z, and we are given not z. And we are asked to derive that y and x are true. So how would we do this? So what we would do, remember our goal here, just to move it down a bit, is y and x. And so how would we get there? Well, first of all, we might use conjunction elimination on premise 1 to derive y or z. Now, we can also use disjunction elimination with 2 and 3 to derive y. Remember, disjunction elimination tells us if we have a disjunction and we know one of the disjuncts is false, then the other disjunct must be true. So we have here y or z derived from premise 1 via conjunction elimination. And then we have, it's not the case that z, we have that at premise 2. And so in that case, it must be true that y, or else there'd be no way for this disjunction to be true. So we can infer y now. And now we can infer x from premise 1 as well, because our disjunction elimination rule says you may take either disjunct. So we may infer x from 1 just as we inferred y or z previously. So now we have y and x. Those are just 2 parts of our goal that we were looking for, which was y conjunction x. So now we can apply our conjunction introduction rule on steps 4 and 5. Sorry, there should be a 5 there as well, 4 and 5. So the two parts of this to derive the conjunctive statement y conjunction x. And that is a valid inference from premises 1 and 2 to the conclusion that y and x. All right, so let's turn to our second proof. So here again, our goal was B or D and C. And we're presented with these two complex sentences. So the first premise is A and B or B and C. And the second premise is it's not the case that A and B. And so we want to derive B or D and C. So how do we get this? Well, first of all, we can infer that B and C is true using disjunction elimination, right? We're presented with a disjunctive statement in premise 1, A and B, or B and C. And in premise 2, we're presented with a negation of one of those disjuncts that make up that first premise. So we can infer that the other disjunct is true because otherwise the disjunctive statement couldn't be true. So if not A and B is the case, as premise 2 says, then it must be the case that B and C are true and that they're what make premise 1 true. So we've inferred at step 3 B and C from disjunction elimination from 1 and 2. We can next infer B via a single application of conjunction elimination of 3. And now if we have B, well, additionally we can infer C from B and C, same as we derived B, just using another application of conjunction elimination from 3. And so now we know B is true, we know C is true, but our goal is to get B or D and C. So how do we get to that? D wasn't even included in the premises. Well, remember, if we know B is true, and we do if we derived it from our premises, which we are supposing to be true, via our rules, which we know preserve truth. So we know B is true. And now anything we disjoin with B will give us a true statement. So we can infer B or D here using conditional introduction from premise 4. And now we are in a position to assert our goal, which is B or D and C. And that follows from conjunction introduction from steps 5 and 6. Okay, I hope that was somewhat clear how we use these rules for our different connectives. Today we explored disjunction and conjunction. Next time we'll be looking at our conditional and biconditional rule. There's one final simple rule though that we might use in our proofs, and that is the rule we'll call R. So if we've shown that something is true, right, or if we know it's true because it is a given as a premise, right, so we know our premises are true, or if we derive something from those premises, we know it's true because our rules are truth preserving, then we can reiterate that thing as many times as we like while preserving truth within our proof. So the general form of this rule is just if you have a line up somewhere above the point you are in the proof that states phi, then you can assert phi, and all you have to cite is R for restatement or reiteration, and cite the premise where this line originally occurred. So this rule is effective for bookkeeping. It's not giving us any new information, but it will help us keep track of different steps as we go along in our proof. Okay, that's it for Unit 9. Stay tuned for Unit 10. See you later.